Push.
Okay. We also have a WhatsApp channel to keep everyone up to date on decentralized AI events, topics, and so forth. This one's far more personal and interactive. Okay, with that, I'll be passing the mic over to Abhishek.
Awesome. Thank you, Rohan.
Yeah, great, thank you.
Welcome everyone to the third roundtable, and definitely join our Slack, WhatsApp group, and also subscribe to the Luma calendar. We are hosting this event every 2 or 3 weeks roughly. So this is the third roundtable, and special thanks to all the organizers for making this happen. And we have a packed agenda with lots of interesting talks. So I'm not going to take away much of time. And with that, I will introduce our first speaker, Ayush Chopra. Ayush is a PhD student, supervisor Professor Rasker. His research focuses on AI and complex systems. He leads the project in large population models and has published in several top-tier AI conferences and has won Best Student Paper awards at multiple workshops and other conferences. His projects has been deployed across multiple countries, resulted in 25 patents, and have been covered by global press. He also spent time at the Mayo Clinic and JP Morgan AI Research. Prior to MIT, Ayush did research on collaborative learning at Adobe and also got Outstanding Young Engineer Award. So very excited to hear what Ayush is gonna talk about. And with that, I'm quickly gonna share my screen. Oh, shared on the wrong screen, I suppose. Rohan, can you see the slides?
Yep, it's opening up in the full PowerPoint layout though.
Right. Okay. Can you tell I'm pressing the right button on?
Yeah,
Play from start.
Yeah.
Rohan, do you still see the slides like the full screen mode now?
No, this is perfect.
Perfect. Okay. All right, ladies and gentlemen, welcome Ayush Chopra.
Hi, thanks. I'm Ayush. I'm a PhD student with Ramesh. And I want to talk to you about building the simulation layer of decentralized AI. So just to give some context, so we live in an extremely complex world. Around 2 billion people cross paths on the public transport on any given day. Around like 100 million transactions are done digitally every day. And we do around 1.5 billion people interact in like classrooms and schools and colleges. We deliver around 100 million parcels a day. So these interactions, like extremely complex, multifaceted, form the foundation of society, but they also become our biggest vulnerability. Like think of 3 years back, where these interactions became the source of the spread of something called the COVID-19 disease, which eventually became a huge pandemic. And it's been a pretty challenging problem, and we spent roughly $1 trillion in the US trying to tackle this problem. Now, this problem is particularly tough because interactions and behaviors of few people decentralized across the world can ripple out and affect millions others. Like think of a simple question like, what kind of a test do you want? So you spend roughly $80 billion trying to distribute tests during COVID, but we still don't have a good sense of what tests are good for the individual and what's good for the society. So think of a simple question. I ask, what kind of a test do you want? You have two options. There is test one, which has like a roughly like a 10% false positive rate, but it will give you a result in 3 days. There is test two, which is like the red pill, which is a 40% false positive rate, but will give you a result in 1 day. And the constraint being, if you test positive, we'll ask you to sit at home for 21 days. So as an individual, what do you pick? It's just like Any ideas, any responses? Why do you pick the, oh yeah, perfect. That makes perfect sense. So as an individual, I always want the blue pill. And in an ideal world, that would be perfect. Like if the moment we take a test, we sit at home, we don't go around and we comply to the constraints of a test, that's the perfect response for both the individual and the collective. But because people move around and infect each other, during the pandemic, what we realized much later is that the government's forced to give people the red pill, a test which is not as accurate. A lot of people who are not infected will be forced to quarantine simply because a lot of decentralized interactions amongst people around the world can ripple out and create a much worse pandemic. So what if you could test drive these interventions before you deploy and spend hundreds and millions of dollars? And that's what we try to focus on. So imagine if you could build like a God's eye view of society, where like if you've grown up playing games like SimCity, things like SimCity, which you can blow up to like millions and billions of agents across the world. And you can track how millions of people around the world interact and how their interactions cascade to shape the world as we see it today. And that's roughly what we focus on. And if you can build this kind of a God's eye view of society, what can you do? For instance, you can use it to determine how can you stop the spread of a pandemic, picking the right interventions, timing the right vaccines, designing the perfect quarantines that are optimal for health and economy. You can also use it to figure out what if a ship gets stuck in the Suez Canal? How will it affect my supply chain as an enterprise? Or you can use it to decongest cities. And to do this, we introduced this new paradigm on AI research. It's called this idea of large population models, distinct from the ideas of language models or the other perspectives you see. And the same way how LLMs are bringing like the simulation layer for generative AI, think of large population models as the pathway to building the simulation layer of decentralized AI. And the insight behind the idea of building large population models is we don't just want to capture the high resolution behaviors of individuals. We want to understand how different people in different parts of the world will respond to a test or want to take a vaccine, for instance. We also want to capture these interactions at large population scales. And doing this requires like a slightly different perspective. We're not just focusing on how do you sense the world in many different ways, which is what most of work in LLMs through language, text, audio, video has focused on, but also capturing how interconnections and interactions amongst people influence how they sense, influence, and evolve the world as we move on with society. And that's pretty much, if you take one thing away from this overview, is the idea is to build systems that don't just try to reproduce extremely smart individual agents, but also grasp the increasingly interconnected world. And think of something like SimCity. If you grew up playing this kind of a game, imagine SimCity, but operating at a billion scale. And we've been doing this for a while, and our tools are now used in a bunch of countries around the world. For instance, we helped the government of New Zealand simulate how a disease pandemic can spread out to prioritize how to distribute vaccines to all 5 million citizens in the country. In India, our tools are helping figure out how can you decentralize an energy grid across 30 million people, incentivizing people to adopt solar energy. Or in the US, we're helping a bunch of institutions trying to figure out how can you safeguard billions of dollars of dairy and livestock supply chain infrastructure against disruptions from climate change, a new pandemic threat like the H5N1 virus, or even just demand and supply fluctuations. And the core insight across many of these disparate problems is to build systems that can model agents at the scale of millions. So you model millions of interactive agents so that you can capture how the collective dynamics emerge across the system. And doing this and building these kinds of agentic simulations in the context of the problems we care about requires solving precisely 3 problems. You want to capture extremely expressive agents. So you're not trying to like make assumptions or trying to simplify the population or assume a lot of people are similar. You want to capture how the behavior of people adapts over time. Like if you ask people to take a test, or if you give a stimulus check in the bank account, how will that affect behavior today, in 3 months, and in 6 months? So you want to figure out how that behavior will adapt over time and across space. Like not everybody might respond similarly to a $500 stimulus check. So you want to capture these heterogeneities in space and in time and behavior. But you want to do that for millions and billions of people in a population. And then you want to see when these people behave independently, how do those behaviors cascade and influence each other? For instance, giving a stimulus check might force somebody to sit at home, but then how does that have an effect on both the labor force participation behavior and in different labor markets, but also the spread of the disease. And you want to capture a lot of these stochastic multi-scale interactions. And you want to make sure that these are not just arbitrary simulations because you want to use them for decision making. How do you synchronize them with reality so that any point in time they can capture the underlying state of the world? So that what's going on in New Zealand is very different from what's going on in New York. And you want to be able to capture that. And we build a lot of tools and software platforms to do this. The first thing we do is, if you've used LLMs as a measure of behavior, and everybody's trying to use LLM agents to prompt behavior, but we come up with this concept of an LLM archetype, which allows you to use LLMs to prompt not 100 or 1,000, but millions and billions of agents concurrently. Imagine like prompting 8 million agents in New York City to just digitally do the census. You can do that with LLM archetypes. And we've come up with a lot of new protocols which allow you to massively scale how fast you can simulate extremely complex interactions over millions of agents. And then we've also used a lot of, and you can bridge these ideas with clever cryptography so that you can essentially like backpropagate through the real world if you're from a computational background, so that you can close the gap between simulation and reality. And you can use like real decentralized mobile apps, like contact tracing apps, to streamline information and signal into your simulations so that you can make very appropriate policy decisions for the collective. So imagine if 10% of the population adopts a contact tracing app, you can still use that signal to make appropriate decisions for the rest 90% today, tomorrow, and in different parts of the world. And we've built tools that allow you to like do this computation very sort of cheaply so that you can scale it up, enterprises can start to adopt it. So if you use like our protocols against like these conventional agent-based simulations that have been used for a few decades, you can get like orders of magnitude in performance improvement in how fast you can simulate large ecosystems, study these enterprises. And we've also built like our own open source platform to bring these ideas to sort of custom users, so that think of it like PyTorch, if you've heard of that, but which is tailored to more large scale agent-based simulations. Like how PyTorch has been like a primary framework to build LLM-based systems. Think of AgentTorch as the platform to build LPM-based systems, which can capture interaction behaviors and dynamics. And yeah, thank you.
Awesome, amazing talk. And we will take questions on Zoom as well as in the room. But folks who are joining via Zoom, please send your questions in the Q&A and we'll take it from there. So while people are asking questions, maybe I'll ask the first question to use my privilege as a host. What other industries or verticals do you see this can be used in? So you mentioned public health, but other.
So I think from an enterprise standpoint, like any problem which has this complexity challenge where like minor disruptions can sort of ripple out across scales, I think supply chain becomes like a really interesting problem. Like supply chain, consumer behavior, energy markets is going to have like a lot of interesting impact on this problem. For instance, I don't know if you're tracking the world right now, but there's something called the H5N1 virus, which is starting to spread around. It's been a bird flu for 20 years, but over the last couple of years, it's now spread to poultry. So you have to cull chickens because they get infected from the bird flu. It's starting to infect cattle. So the milk is infected, and that eventually sort of trickles up to pasteurization plants and the distribution network, and eventually to like consumption. Like if you go to Whole Foods, like eggs are $10.99. It's probably because we've killed 100 million chicken over the last 2 years. So all problems have like this very multi-layered and interconnected nature. So definitely like supply chain, energy networks, all of those things will have like relevance to these kind of problems.
Awesome. Any questions? Go ahead.
So I have two quick questions. The first is, how is this qualitatively or quantitatively different from work that was done, let's say, at the Santa Fe Institute 20, 30, 40 years ago, ABMs?
Yeah.
And the follow-up is, I worked at IBM in the 2010s, and there was a sort of famous project where they built an agent-based simulation of Portland to do, disaster relief rehearsals and things like that. My experience, and I'm a fan of this methodology, is that a lot of these techniques are good as like education tools, but they sort of fail in terms of being a predictive model or anything like that. And I'd just like to know, are there new formulas or techniques or results that make you believe that these could go beyond the scope of just sort of like rehearsal apparatus?
Exactly. That's
Can you summarize the question for the audience also?
Okay. So the primary question is like a lot of the work that we're talking about builds on top of this paradigm of agent-based models. And like the question is about how is it quantitatively different, and how do these ideas sort of take agent-based models beyond the lab into more of a predictive, commercially viable solution. And exactly, and that's the primary focus of this work. Okay, I think we lost that, but there are like a few things. The first reason why those ideas were not scalable, and like that's where we started working on, is they were not computationally scalable. For instance, when we started, we did some work for the UK NHS, where they wanted us to build like some kind of an agent-based model of London. And when we built this kind of a system, one simulation would take like 50 hours to execute, which means you can simulate like a few hundred agents, but like if you want to build realistic simulations at population scale, they would be like extremely slow and efficient. And by the time we were done with that collaboration, we bought like 50 hours to 5 minutes. So now you can actually simulate like real enterprises on your laptop. So like hardware has come a long way, and we can like leverage a lot of the ideas that make like neural networks and deep learning work through like vectorization and a lot of tensor programming allows us to run these simulations more efficiently. We've invented a lot of protocols which allow you to sort of quote unquote differentiate through these simulations, which allow you to like plug and play them with neural networks. And then you can use the gradients for a lot of cool calibration analyses, which allow to make sure that you can actually calibrate them to real-time streaming signal. Like if I go to New York City, I can recalibrate my model to how fast disease is spreading, what are the qualities of the variants here, what information I know about social behavior, and a lot of multimodal signal. So we make that possible. And the third big thing is that we sort of synchronize them with like physical infrastructure. So like if there are contact tracing apps, our protocols can essentially like get the gradients from the real world, not just like demonstrative simulations. You can track as like the world goes through phase transitions. So like, I put in an intervention, now suddenly you'll see like I gave everybody a stimulus payment. Suddenly there's like a huge fall in mobility of patterns of people. So because like your simulations might not be able to capture that phase transition, but contact tracing apps are like physical protocols too. So we like synchronize with physical protocols on a real-time basis so that you can streamline information from there. So you have like a very granular sense of interactions at multiple layers. So there's a lot of work. And we've actually shown in a few papers that these can actually predict better than neural networks for longer range horizon tasks. Like if I'm trying to forecast multiple waves of disease, so you can capture how disease goes up and down, which you might not be able to do with the conventional method, which cannot sort of model changes in the world.
Okay.
If the simulation is cut off from real-time data, how long will it diverge and the potency as a predictive tool like
that's a function of the underlying dynamics. Like if it's disease and the world is changing very rapidly, you want to like recalibrate ever so often, because like suddenly the rules of the game changed, which is why like neural networks are not a great idea for that problem. Because if you try to predict time series to time series data, that won't work, because like the virus changed or suddenly something fundamentally changed in the world that you can't account for. But like, because you can account for that in these systems, you can actually relatively predict for longer horizons than more conventional data only models. But again, that's a function of the dynamics that you care about.
Any other question? Okay. We'll
You mentioned if they acted independent, do you have ways of dealing with collusion?
In the
between
context.
agents? You mentioned that, you know, you can do simulations when the agents are acting independent. But so you have mechanisms or ways of incorporating where they are colluding, right? Or
Yeah, you can model a lot of different interaction patterns. Exactly. You can model like how people, if a disease is spreading, you can figure out like,
yeah.
oh, sorry. Yeah, so you can model like interactions at multiple scales, like at work, at school, for instance. If you're trying to track how disease is spreading, so you can model interactions let you help figure out collusion.
Okay, we're tight on time. So one last question. Go ahead.
So I understand it provides a snapshot and a dynamic real-time snapshot with understand the degree of impact. But how does it connect with the actual methodology of, consumption and recovery at the time?
Okay.
Can you repeat the question for the audience?
Okay, so I think so. If I'm getting it right, so the question is that the simulation platforms can tell you what's really going on in the world, but how do they translate to real action on the ground? Is that?
But at the time of the disaster, okay, maybe it replicates and you can see the snapshot in a dynamic way. But how does it transfer? I mean.
Okay, I mean, I can give you reference. I can give you a reference from a real problem that we've been solving. So what happened? Sorry. What do you mean by critical infrastructure? Okay, so I can give you example from this problem we are on the ground tackling these days. So after COVID, there was a lot of vaccine hesitancy. So what we're helping like the government of New Zealand figure out is like, how do we get people other vaccines, like the measles vaccine, which is perfectly fine, fully sterilized, it'll always work. But a lot of people don't want that anymore. So the problem they have is like, oh, we've got $100 million. How should we start vaccinating? Like, who should we, like, usually incentive subsidies work. Like if you go to like communities and say, we'll help you, like, we'll give you this infrastructure, we can deploy a lot of these resources, they might be like incentivized to adopt it. So now the question is like, how do we go across the country? Like, how do we sort of prioritize our plans across different regions in the country? And what these tools are helping them figure out is like, oh, you start with region A, B, and then C. And that's how you can traverse. Given all the constraints they have, the public, it's sort of a communication mechanism between the engineers, the scientists, and the leadership. So yeah, I mean, it's not going to go on the ground and do the task, but it's just sort of helps you test drive things before you really go and deploy them, because these are often like irreversible challenges. Like it's not like an A/B test. Yeah, exactly. But for sure, like somebody has to do it on the ground.
Okay. Okay, thank you so much again, Ayush, and let's thank the speaker. Definitely check out Agent Torch. And Rohan, can you share the slides again? And sorry, we couldn't take the Q&A in the Zoom chat, but we will return to that. Hopefully we can find time later.
Abhishek, is it me or Rohan? Like, who is gonna talk? Is it me?
Yes, we are gonna introduce in a minute, so just give me-
Okay, because I can share my screen.
Yeah, can you share your screen then? Yeah. So yeah, okay. So for the next talk, we are really excited to have Antigone present. And Antigone is Executive Director at JP Morgan AI Research. She heads the JP Morgan AlgoCrypt Center of Excellence, holding a PhD from Aarhus University and a postdoc from Cornell. She has received several awards, such as Junior Simons Fellowship, and is a named prolific JP Morgan inventor. Her team's cryptographic tools, leveraging new privacy-preserving algorithms, are reshaping the landscape of data utilization in finance. So very excited to hear from Antigone. Stage is all yours. Let's thank the
Great,
speaker.
thank you. You hear me right?
Yes, we can
Okay.
hear you. We also see your slides.
Okay, perfect. Okay, so this talk is about private decentralized AI. Wait, let me remove this bar away from here. And as we know, AI is everywhere, but here we care about the privacy concern. What if our data is stored in different silos and we cannot bring them together? Or another case is that, let's say we don't have the computational resources to run these AI calculations and we want to outsource our computation, but again, our data is very sensitive and private, so we cannot really outsource our data. And to achieve these goals, essentially we use tools from cryptography. And in general, you know, everybody uses cryptography, even you use it every day. But here, what is important is that we want to compute secure computation on the data, okay? So we don't just exchange encrypted data as we do online every day. We just really care about performing computations on the encrypted data without revealing anything about the private data. And I have two scenarios here. Let's say we have like in the same company, do different departments, they want to train a model, but of course they cannot exchange the data. So we can use secure computation techniques to help them come up with a combined model, for example, to detect fraud. Or you can even have in the institutional companies, like different companies, again, they want to build up a model. Again, they cannot exchange their data. So there is where we can use secure computation techniques. And then another scenario is that somebody has the model and somebody else has the data. And now whoever has the data wants actually to query the model, but without revealing the queries to the model and get back the answer. And there are many different scenarios that I can actually tell you and go over them like for multiple hours. But in general, all of these different use cases, they call for secure computation, okay? And there are also like some other techniques that cryptography can actually be used not only for computations, but also to actually help in AI misuse. For example, if deepfakes, you can use digital signatures for deepfakes. You can do cryptographic watermarking and also like check the bias if a model is biased. Let's say you don't have access to the model and you're a company and you want to use that model, but you want to see how fair is that model. But again, you don't have access to the model. How are you going to do that? Again, you can use techniques from cryptography and zero knowledge to be able to enable these use cases. And in general, I'm at AlgoCrypt Center of Excellence in JP Morgan, and we care about all of these use cases that I just said. First, we try to secure the data, and then once we have the data, we want to actually perform secure computations on the data. You don't need to read the slide here. I just have it here for reference. And once we know what computations we want to do, then we need to ask where we want to do these computations. What platform? Is it on the cloud? Is it on the blockchain? Do we want to do it in a way that is quantum safe? So this is like the topics that we're interested in JP Morgan. And in general, let's see what is the state for cryptography and machine learning. So, I mean, secure computation was introduced in the 80s. It took a lot of years to make it practical. Today, we have some practical use cases, for example, federated learning, which is what I will focus more on this talk. And then when we talk about MPC, okay, just plain MPC, for example, auctions, okay? When in 2008, there was this famous sugar beet auction that happened in Denmark. So apart from this use case, there's this MPC dashboard. You can go and check. They have gathered all the use cases, the real world use cases that we apply MPC. Most of them actually are wallets, okay? So definitely MPC is not mainstreamed yet. And we also have here in the bank, actually we're the first bank that we use MPC for auctions. You can actually access the paper here, prime mats. But apart from these cases, like the prime mats that we have, which is like encrypting orders and trying to match them, and we also use secret sharing on wallets and all of that, we don't have a lot of use cases. And now if you're gonna ask me, okay, so what about doing encrypted LLMs, like AI computations are even more complex, right? So what is the state for that? Do we have practical solutions? The question is no. So we don't have very practical solutions. We have under some use cases, I will just mention now, but we still need some more time to make these tools more efficient. For the use cases that somebody doesn't care about the running time, definitely these tools can be used. But if you want to do, for instance, Q&A with a chatbot, okay, or an LLM, I mean, Q&A, you have to be there. You need to get an answer back fast. The tools are not there yet to do these techniques, okay? And here I have this encrypted LLM. So let's say we have, we are working on this where we have the LLM provider and the company or a user. So they don't have the computational resources to run a model. So think that the LLM provider can be OpenAI or you can name it. So we outsource our computation to this LLM provider. So we have a query. So we want to hide and encrypt our query, okay? Whether our query includes sensitive data or even the query itself has to be secret. So we are encrypting the query. Then the encrypted query goes on the LLM provider. Then they are supposed to operate on this encrypted query and give us an answer back encrypted. And we are the only ones that we can decrypt. Okay, so this is the use case that we're working on. And for that, we're using full homomorphic encryption for those of you that you're familiar with it. And in general, this one thing that I have to mention. So we need to change the LLM to make it work on this encrypted data. For example, if you go now and actually put an encrypted query to an LLM, okay, so this is an example from ChatGPT. Like I put here an encrypted message, okay, so look at the answer of the ChatGPT. I mean, it doesn't recognize anything. So we need to change the encrypted LLMs to work on encrypted data. So it's not like trivial. So the thing that it doesn't really recognize encrypted messages. Encrypted messages are supposed to actually remove any structure of the data. So we have to, in general, change the model. And as I said, so we have a work that we're working on this with Leo De Castro and Daniel Escudero from JP Morgan. So what I can tell you from now, I mean, the paper will be online this month, but in general, this tool is good actually if you want to do, let's say, summarization. So let's say You want to have your document encrypted. So, okay, so you don't want to leak your private document, and then you ask a summary of it. So for the use case that you are okay to wait, these things are there. But if you want something more active, back and forth communication with the LLM, it's like, it will not be really efficient. There are some other MPC solutions where you can have you split the LLM provider to multiple parties and you apply MPC instead of fully homomorphic encryption. But then you start asking the question, how far are these LLM providers? You need to add actually the delay between the messages that they need to exchange. So at the end of the day, if you consider again a real practical scenario where these providers are in different places, it will still not be very fast for Q&A, okay? I'm gonna skip the slide. So, and in the rest of the time, I'm gonna tell you about our work on federated learning, where again, so here we have again multiple parties. You can call them agents. They basically do some training. And this is a very well-established problem. And as I told you, it also runs in production in some companies, okay? So I will go very quickly over federated learning because I assume that most of you are probably familiar with it. So we have a bunch of users, they want to train a model, and a server in the middle wants to come up with a global model. So the clients train their own model on their devices, first getting some global model as a basis to start with, okay? And then they send their weights to the server, and the server sums them up, gets the average, and gets a global model. And then we keep repeating this process for multiple times, okay? And what is the size of this population? So it can be like 1 million devices that we can have, okay? And per training, we can call up to 5,000 users to come in every training iteration to participate. So these are large scale numbers. And I'm not gonna go in detail over the applications, but as you see here, it's used a lot. You can come up later and look at the applications. But the main point here is that where we use cryptography here is that the weights itself can actually leak information about the data. So we can encrypt the weights, okay? And the goal is to have the weights encrypted and do all of this process in a secure way, okay? So in the interest of time, I'm gonna go a bit quicker here. And our team also has worked a lot on this setting of secure aggregation for federated learning. So the first seminal papers came from Google. And in fact, our protocols, so these are our protocols are like 100 times faster in general end-to-end time. Also the bandwidth is 200 times more. And another important thing is that we reduce the round complexity of these protocols. And at the same time, we have the same security guarantees that these protocols have. Okay, so we have different versions. For example, microsegag was our first work. This one is great, but it only works for moderate size models. It's not great for very large models. Then we have Lerna, which is good for a quantum safe solution. And then Flamingo is the one that is better for large models. Then we have a more recent one, which we call OPA, where this comes very close to the baseline unencrypted federated learning, where in the unencrypted federated learning, you send a message to the server and the server just aggregates everything. So it's one round of interaction. So in this work, we also try to do this one round of interaction also in an encrypted way. The first papers of Google, they were using 8 rounds of interaction, okay? So it was a lot of back and forth. And we also have this work on Mantilo where we are trying to put some checks on the inputs of the clients, such that like input validation, so that they cannot submit weights that they are like completely like out of range and all of that, okay? So it's just a form of checking. We cannot check all of the possible attacks that they can do, as you know, but this is just for specific input validation of the inputs. And just I have a quick, just to give you an idea on how these aggregation protocols work. As I said, like everybody has an input thing that these are the weights, and we have an aggregator and we want to get the sum, okay? So in general, how all these protocols work and the Google works that the first came out. So you add the masks to your inputs. That's how you encrypt them, okay? And now you send your masked inputs to the server, okay? And then somehow the server aggregates everything. So you see all the masks here are there. So somehow the server needs to remove these masks to get the actual sum, okay? This is the goal here. And the first Google papers, how they did it, they had these masks such that if you add them all together, they sum up to 0, okay? So now if we go back to the slide, when you send the encrypted messages, because they have it in such a way, they have the setup phase that this message is equal to 0, then you can essentially get rid of these masks, and that's how the protocol works. Okay, but you needed to spend a lot of rounds to set up this setup to have these masks equal to 0, and there are some other problems. What if one client drops out, so we are missing his mask, then we will not get the sum of the masks to be 0. So they had to come up with this with approaches to overcome these issues. And in general, we have 3 phases: the setup phase, where you actually construct the mask; the masking phase, where you mask your inputs, and somehow you need to unmask to get the sum. Okay. And as I said, I already mentioned, this is the first work from Google, from Bonovitz, that they achieved this. And then they had another work where they made this a little bit more efficient, where the setup phase was more efficient. In the previous setup phase, every client had to talk to each other. In the 2020 work, they only had to talk with some like neighbors of them, like only log a number of the users, not all the users. And something that we started introducing in our works is that this masking that you have to have around to mask your input, we came up with an idea to reuse the mask. I'm not going to tell you how we're reusing the mask, but that was the big idea here. And because we reuse the mask, we can also have less rounds of interaction. And then the first work was working for small models. And then we have these other 2 works here, where, again, we are based on this idea of reusing the masks. And one of them works for, and it's secure under quantum safe assumptions, and the other one is based on standard assumptions that we use now that they're not quantum safe. And they're good for large models. Okay, but also the round complexity of this previous works that we also have, this Flamingo and Lerna, as you see here, it's 7 rounds, and Lerna is 3 rounds. So in this other work, OPA, we really have like 1 round. The clients sent 1 message, they encrypt the message. Then there's another message from some other parties, which we call committee. And essentially you have 2 rounds. So it's getting very close to a non-interactive solution, okay? And these are actually the works, you can find them online. And as I said, we also have Armantillo, where you can now check the inputs of the parties such that they don't submit malform inputs. And yeah, you can find these papers online. And yeah, let me know if you have any question, but in general, as I said, federated learning is something that we use in practice. And as I said, the other works that involve LLMs and all of that, they're a little bit only good for specific use cases. So yeah, thank you.
Speaker. Okay, once again, I'm gonna use my privilege as a host to ask the first question, but meanwhile, send your questions on the Zoom and we'll take the questions from audience also here. So my question was about, initially you mentioned that you have to change the neural network architecture or something about them so that they become compatible with encrypted computing. Can you talk more about that?
Yeah, and actually that can use 1 slide to say more about these things. So this question is very interesting because many people have this question, okay, I mean, if you encrypt the data, it's still data. An ML model is supposed to understand data, so why it doesn't work and why do you have to change the data, right? So the thing is that, as I said, like you completely destroy all the structure when you encrypt data. That's the job of the encryption. You introduce randomness to the encryption to completely destroy all the information. And because of that, if you run, I don't know, let's say your model has a GLU function, a sigmoid, okay? So if you run that on this encrypted data, I mean, you will get nothing, right? Because now the data is very like, you lose all the structure. For example, here I have an example. So here is the raw data. They are unencrypted. This is a classifier. It's actually an NN. Okay, so this is the raw data unencrypted. So now I encrypt them and I run the same model without changing the model to work on encrypted data. So you see here I'm getting, like, I'm not getting the right classification, okay? Because my data is encrypted. So I need to get the sigmoids or GLU or whatever you're using and actually make it understand these encrypted messages, okay? So this is the whole thing. So you really have to change, let's say there's a multiplication happening here, you need to replace it with a secure multiplication that understands encrypted messages. So this is the general idea. So how we do it more concretely is another story. For example, with fully homomorphic encryption, when you multiply things, it has to be done that recognizes this encrypted ciphertext, right? So how you multiply the 2 ciphertexts is different how you multiply the number 5 and 3 and how you multiply an encryption of 5 and 3. So yeah, so that's why we need to change the models.
Very interesting. Any questions here in the audience? Okay, there you go.
So they had something accurate data then, and so it seems like that happened where how easily could they be fixed?
Yeah, so maybe I can summarize the question. It's about like sometimes you'll have incorrect data or some other issues. And when it's in plain text, you can see the problem and fix them. But when things are encrypted, you cannot. So the question is, how do you take care of those situations where data might be faulty, incorrect, or even the model might have some problem?
Yeah, that's what we started doing in this Armantilo work, where basically, as you said very rightly, that yes, you cannot see the data, right? But whatever computation you could do in plain text, you could also do it in an encrypted way. For example, we're computing the L1 norm, the L2 norm of these data sets that you get. So we can do that in an encrypted way, okay? So, but if your eye can see something else which is not L1 norm and L2 norm, yes, this is not covered. So that's a big issue with these approaches. For instance, a medication for federated learning is actually the following. There's something called robust federated learning, where they try to make the weights to be either 0 and 1 only, and have actually the same accuracy as if your weights were actually different, not only zeros and ones. And in that case, you can cryptographically check actually if your weights are zeros and ones. And in that way, you can actually get rid of this problem. But again, like for example, to use this RSA, maybe you need more iterations to reach the same accuracy as you would do before. So there are some ways to do it, but yeah, nothing is better than the eye. But think that for some computations that we can do in the clear text, we can also do the same computations in an encrypted way. But yeah, the best solution, as I said, is this robust federated learning, because the entries are only zeros and ones, and there we can do it better in an encrypted way. You can have a look into that.
Cool, thank you. One question in the Q&A is, can similarities be computed in encrypted text?
When we say similarities, we mean
So like
how
you want to
far?
analyze similar text essentially, but
Oh.
it's encrypted. So
Yes.
like ancient current protocols are, maybe that's the question is about.
Yeah, so you can do that. So you can find similarity also in text, as you find like, you can convert your text to a numerical space, and you can definitely do that. So yeah, you should be able to do it. So think that if you have an algorithm that you can do it in the plaintext algorithm, in the plaintext space, we can get the same algorithm and put it in an encrypted way. Then the question that you should be asking, okay, how efficient that will be? Will it take me like a second? Will it take me like 1 minute? But the similarity is very fast. It will be very fast. Yeah, we can do this type of computation fast.
And let me generalize that question broadly. So can you give us a sense, like the general criticism of these homomorphic encryption or even multi-party computation approaches is it's inefficient for many interesting applications in machine learning. So can you give us a sense of like how things have improved in the last 10 years and what things are currently practical? And I know you mentioned that like if you want to do LLM inference right now, it's sort of impractical. So can you give us a broader sense and how quickly things are improving? Because maybe today it's not possible, but maybe 1 year from now it might become possible.
Yeah, and as I said, I had that chart there, right? So there were so many years that things were improving. For example, I mentioned the auctions earlier. In 2008, it was the first auction that used MPC in Denmark. So that time, if you go and read up the paper, it took several minutes to do that computation. And that was in 2008. And for example, today that we do auctions with primats, it takes like seconds, okay? So you can see that in almost like 10 years, we were able to come up with new algorithms that they're much faster, okay? And for, let's talk now about fully homomorphic encryption. Also, like if you see the progress that happens in the last 10 years, like people come up with faster algorithms for bootstrapping and all of that. And there's even effort with hardware acceleration to even make FHE faster. Actually, I had some slides in another presentation to show you like how fast fully homomorphic encryption bootstrapping has been improved. And actually it's been improved in the order of the thousands in the last 10 years. So it is getting closer, but I have to say something too. for example, what I was saying for the LLMs, right? That you can run now this summarization queries, right, on encrypted data. I'm assuming in our work that I spoke about, we are doing everything on GPUs, okay? So also, I mean, if you think about it, also like the clear text models today, they are run on GPUs, okay, because they are huge. So the running times that I'm using, and I'm telling you we can run summarization, is on GPUs, okay? If you want to go to CPU, that's even worse, okay? So you will have to wait days to do that if you go to CPU. So it's getting closer, as I said, and even for neural nets, before LLMs came around, right? So we also had a lot of MPC works and FHE works for neural networks. I mean, you could do things in seconds for some use cases based also on how large were the models. But again, like, I mean, FHE was always lower in the sense that than MPC because of the computation overhead. But for MPC, calculations are faster. But again, if you, in MPC, you need to spread up your trust, you need to have at least 2 or 3 entities to do the computation, right? But again, there, like if you put it for a real world use case where these servers are in different locations, I think then it might be like actually slower than using fully homomorphic encryption, okay? So it depends what you want. And also another thing is with full homomorphic encryption, it's much harder to get what is called malicious security. If somebody deviates from the protocol, you want to catch them. This is very expensive to do with fully homomorphic encryption even today, maybe in 10 years, that will be better. There are some efforts actually from some companies that they're trying to make malicious FHC better. Malicious MPC is very fast. It's the same as non-malicious MPC. That's very good. So I would say depend what use cases you have. I mean, we're getting closer, but if you see what happens today, we really, I mean, we don't have any real use cases that use neural networks and all of that. I mean, we have federated learning, but federated learning is you run the AI locally, right? What you run in a decentralized way, just a secure aggregation. So it's getting there. Since 2020, we have seen like federated learning and more use cases are coming up. And also we hope with these auctions, people will get more used to MPC. For instance, I'll give you an example. When I came to the bank and I told them to do these auctions, and I said, we're going to use this MPC technique. And they told me, okay, who else is using MPC? And I'm like, well, I didn't have any example to show. So it's also hard. If something is not mainstream, people are not using it, right? So I think it's getting there slowly. And you can also see this MPC dashboard as I show you to see the use cases that they're going there. So I think in 5 years, we'll definitely have more real world use cases. So it's getting closer, which is very positive. But yeah, like for some tasks today, it's not great.
Awesome. Do you want to talk about a little bit of and compare with computational computing, secure enclaves kind of paradigm?
Oh, yeah. So if you combine actually MPC with secure enclaves, that can be very fast, okay? Or like even like the combine. So you cannot, I mean, you can use only secure enclaves, but there's based on the use case, but for most use cases, there is an issue. Your secure enclave needs to go and fetch some stuff from the memory, okay? So you need to go outside and fetch stuff. So this fetching can create actually leakage. So you need to actually usually combine your secure enclave with ORAM, this oblivious RAM. So that can actually slow it down a bit because now you will have to do that. So that's why I'm saying the best is to have a combination of the secure enclave and secure computation or FHC so that you don't put your whole trust on the enclave. So if something happens with the enclave, I mean, you see attacks almost every day. There was actually 2 weeks ago another attack on Intel SGX. So you can actually find a way to use the practicality of the secure hardware, but at the same time also use secure computation in a minimal way such that you don't put your whole trust on the secure enclave. So you kind of split your trust. So that can be more efficient, but just I believe you have to combine it with some secure computation too, in a minimal way to actually gain from the computation of the secure enclave and gain also security from the MPC or FHC side. So a combination of the two is ideal.
So one interesting point I'm seeing is, I think this is what you were mentioning, right? Like you're doing computation, but you also need data from memory, and that's where secure enclave might not be completely secure. So you need to couple it with something like ORAM. Again, would require some kind of homomorphic or MPC again.
Yeah, so you can either use standalone ORAM or also like you can find other ways that don't use ORAM and use just MPC and FHN and secure enclave. But yeah, the point is that you need to combine it with something else to use it.
Okay, one quick last question from the Zoom. I'm sorry, we're running out of time. So the question is about, yeah, we looked at one of the questions. So it's about, is there a cryptographic way of using these cryptographic techniques to distinguish between AI generated content versus like real actual data generated from users?
Oh, okay. So that's a very interesting question. For instance, I mean, I read an article recently and it was showing real generated data and fake data. And they were asking if I can tell. So even sometimes the real data was saying that they're fake. But anyway, so what you can do cryptographically, you can add cryptographic watermarks. Okay, so to do that. But there are also some other ways, for example, for deep fakes, like for ownership. So if somebody comes and Abhishek comes and says, hey, I generated this content, okay? We can use digital signatures for that, okay? But if you say, Abhishek created the content, but Abhishek comes and says, oh, actually, Ramesh created this content, okay? So on behalf of Ramesh, you're creating something that Ramesh never agreed, okay? But if we have this digital signature, then I would go to Ramesh and say, hey, Ramesh, give me your key. I want to verify if this content comes from you. So if the content didn't come from him, the digital signature will help me figure out. You cannot forge the digital signature. So that's a very good use case of digital signatures claiming ownership, okay? So that's about ownership. So now if you just give me data and I'm supposed to just look at them and tell what is real, what is fake. I mean, if it doesn't have watermark, and in some cases, the cryptographic watermark, there can be some edge cases that you can actually remove it, okay? So then it's very hard to tell. There are some works that they are saying if you start and modifying content that exists already, for example, you can have some keys on your phones or on your iPhone that generates the picture, and then let's say you get that picture or video and you change that part and you claim that it's real or fake. We can find out if you start from that content, but if you start something completely from scratch on your side, it will be very hard. But I think the part of ownership is somehow resolves this issue, because usually you will do this content to blame somebody else. So in that part, ownership can be solved with digital signatures. But if you try to create fake ads that go everywhere over the internet, that will be much harder. You can use the cryptographic watermarks. In fact, we also have some work on that, but there could be edge cases that you could potentially remove it. We don't have the great solution that, because if you modify it a bit, maybe you are lucky and you remove the watermark. So yeah, it's that's a hard task.
Okay, so let's keep it quick.
Question on our perspective on possibly peer-to-peer federated learning server less.
Yeah, actually, that's a great question. I also wanted to ask.
What is the question?
So the question is about your perspective on like generally peer-to-peer federated learning, or even like any other decentralized protocol where you don't have like a traditional server facilitating communication among clients.
Yeah, I think that in terms of like real world applications, so I mean, I've been trying to do this in finance with different banks, okay? Bring together different banks so that we can do this peer-to-peer between the banks. It's not successful yet, like trying to make them agree to run these computations. But I think it should happen in the future. There's no use case yet there, but if we can do that, actually we can have faster protocols. That's true. Because in the single server secure aggregation, you have this point of failure, a single server. So the protocols that we come up with, they're a little bit more complex, but yeah, if you use peer-to-peer, then the protocols are a bit more faster because you can use secret sharing and all of that. So in terms of efficiency, it will be a bit faster than secure aggregation, although single server secure aggregation is getting very practical now. But it's still like malicious security will be better with this peer-to-peer federated learning. I think these use cases will come up just like in a real world setting. You need to convince two different entities to do that. And again, they have like some restrictions, or like you have to convince them. Okay, it's not about like, so there is like this hard trust in these secure computation techniques, but now you also need to convince the companies to do that. So, but yeah, I will see that in the future happening as we have more use cases of federated learning or MPC. People, as we have MPC more mainstream, I think different entities will be convinced to do that.
Awesome. We're running out of time, so we'll keep these many questions, but let's thank our speaker again.
Thank you so much for the invitation.
And now we will move to a very exciting panel session. So Rohan, do you want to share your screen again and load the panelists? Awesome. Just give me 1 second so that I can promote the panelists. Oh, sorry. And. All right. So we have our panelists now. So the way this session is going to work is we'll have quick 5-minute talks from all 3 of our panelists, and then we will have a Q&A session, and also we'll ask some questions, the starting point. So we have 2 panelists joining us remotely and 1 panelist joining us in person. So I suppose, okay, this Zoom goes away every time. We will start with our in-person panelists first. So Levi has been working in the intersection of mechanism design and distributed computing since 2017. Most recently, he was at Protocol Labs, conducting research on game theoretic verifiable computing and autonomous agents for pricing and scheduling in distributed computing networks. He's now the founder of CoopHive, which is building a generic machine actionable marketplace. Welcome, Levi, and let's load up your slides. Rohan, do you see the slides? Can you confirm?
Yep, I do.
Okay, perfect. Levi, stage is all yours. Let's welcome our speaker.
Hi, my name is Levi Rabalov. I'm the founder of CoopHive. So I'm going to give an overview of what we're building, how we got here, and where we're going. So we originally set out to create a distributed computing network with optimistic verification. For those of you who don't know, there are 3 main categories of verifiable computing. There are cryptographic approaches that include zero-knowledge proofs, multi-party computation, fully homomorphic encryption. The second category are basically secure enclaves, like trusted execution environments. And then the third method is verification by replication. So you redo the computation, you see if you get the same result. Total side note, basically preventing cheating in distributed computing networks basically comes down to preventing collusion, which is a very, very deep problem, but I'm not going to be going into it in this talk. So basically what we settled on for our architecture was a sequence of IPFS CIDs. And so for those of you who don't know what IPFS is, it's basically a peer-to-peer file sharing system where you identify things by what they are, not where they are. So basically you take some file, you hash it, that hashes the identifier, and then you use distributed hash tables to find the file basically and retrieve it. And so basically, what we settled on was basically maintaining a record of IPFS CIDs on-chain, on the blockchain, and then using those as pointers to arbitrarily large off-chain data. So what you basically end up with is a very lightweight data structure that can really model really any, very, very simply model like any kind of deals, mediations, results, and so on. We had a pluggable mediation protocol so that you could really kind of plug in any verification protocol, not necessarily just repeating the computation. But as we'll see, that comes with some complications. And then market making is done via an off-chain solver. And so what that basically means is there's a set of clients, there's a set of compute nodes. These people need compute, these people have compute. They send their offers and requests to the central to an entity known as a solver, which is a market maker. It maintains an off-chain order book. It proposes matches to the two sides. If the two sides agree, they make a deal. That deal is put into an IPFS CID. The CID is put on chain, and then of course the result is put on chain, and the mediations are also put on chain if they happen. And then we have payments for the job is made in a single ERC20 token. Now this came with some challenges. I'm only going to go over a few of them right here. But the first one is that single token limits adoption by locking in users. So a lot of the reason that people got into this space was that they wanted to avoid vendor lock-in, but a token lock-in acts very much like a vendor lock-in, and it really prevents a lot of interoperability across systems. The second problem is it's unclear how clients and compute nodes would actually accept or reject deals proposed by the solver, by the market maker. There's really kind of like no logic in that system. If you could just trust the solver, but then now you have this like massive like centralized point of failure. And for those of you who are familiar with the problem of MEV, maximal extractable value, that also happens in this environment, and it can get quite tricky and quite painful. And then the third problem was that we, in doing the research on optimistic verification, it turns out that we need the ability to have very modular job life cycles. We need to be able to include particular types of collateral at different points in time, and then test out different combinations in order to prevent malicious behavior. So how did we approach these? So the first thing we did is that we decided to take an agent-first approach to designing the protocol. And what that basically means is really taking this concept of utility maximization, which is core to game theory, and really imbuing it into the protocol and thinking from the perspective of an agent that is constantly trying to maximize utility. So in the case of a compute marketplace, and I'll get in the next few slides, I'll get into why I'm specifically describing the compute marketplace. But in the case of compute, you can use these agents for pricing and scheduling. So you can imagine I am a compute node. I have a bunch of offers coming in. I have a limited set of resources available. I want to maximize my revenue. This is a classic scheduling problem. And of course, scheduling and pricing are intertwined in this environment because I might be willing to pay more for a result that comes sooner, or I might prefer to pay less for a job that happens at 4 a.m. because that's when electricity is cheaper. And then in addition to that, we can also reframe the verifiable computing problem in terms of the utility maximization. So this would be a long aside if I went into it, but basically one of the conclusions I came to during the research I was doing was that trying to find an analytic solution to the problem of optimistic verification is not really a great idea. The reason being that naturally you have to make assumptions in your protocol, and in the real world, those assumptions, some of them are not going to hold, and then your theoretical guarantees break down. So we decided not to take an analytic approach, instead taking an empirical approach. The basic idea is you take agents, you train them in this environment to maximize utility, and that would include cheating and colluding if necessary. And then you can incrementally add in different anti-cheating mechanisms to see what actually prevents cheating and collusion. Now, there are problems with this approach. You can look at the multi-agent reinforcement learning literature and realize, okay, you might not actually converge to an equilibrium, et cetera. There are problems with this, but for reasons I can't get into, that's the approach we decided to take. We also decided to replace market making with agent-to-agent negotiation and agreements. There was a bunch of reasons for this. The main reason being that agent-to-agent communication forms the backbone and the foundation of multi-agent systems. And you can recover solvers, intermediate market makers from that kind of system, but it's kind of hard to do the reverse. So the basic idea is that something like a market maker should emerge naturally as an emergent phenomenon from the scalability limits of agent-to-agent negotiation, rather than being imposed from the outside to begin with. For the modular job lifecycle, we decided to go with a series of credible commitments that allow modeling any collateralization process, which means we can model many kinds of marketplaces. The basic idea is money goes into escrow, something happens, money moves out of escrow. That's the basic pattern. And if you model it that way, you can actually model many marketplaces, not just compute. And then, of course, in terms of the problem with having a single token, well, you can just imagine generalizing a bit. Well, okay, we can say instead of paying in one ERC ERC1 fungible token, which ERC20, you can pay in any fungible token. So now you can pay in any ERC20. And then you can say, you can generalize that a bit and say, well, if you can already pay in any fungible token, why not allow also paying in any non-fungible token, right? And so now we can include ERC721s. And then, of course, there's a few more token standards, 1155, 6909. Those aren't really kind of relevant. The kind of important idea is you can now pay in any fungible or non-fungible token, meaning that you can represent many different kinds of assets. So for non-fungible tokens, you can represent assets on eBay or Amazon. You can represent, kind of really any real world asset that you want, which, enables kind of a lot more flexibility. So what that basically creates is, a generic marketplace protocol that's based on the three primitives I mentioned. So there's the ability to exchange bundles of assets. Oh, I actually will go back here. Talking about exchange any asset and then exchange any bundle of assets, right? And so for those of you who are familiar with some literature on cooperative game theory, there's like this kind of really dormant literature around exchanging bundles of assets, which is really, really fascinating, but which hasn't really been used in practice to the extent of my knowledge. And we're trying to enable that. So yes, the outcome is basically a very flexible generic marketplace protocol based on three primitives. The first is the exchange of bundles of assets for other bundles of assets. A series of credible commitments that can model any collateralization process and thus any kind of marketplace. And then agent-to-agent negotiation. And so regarding the marketplaces, right, like, of course, we can have a compute marketplace. That's what we're starting with. But it's not hard to, extend to the other two really critical parts of the tech stack, of course, which are storage and bandwidth. And of course, we can also have, data marketplaces, real-world asset marketplaces, peer-to-peer energy trading, synthetic assets, and so on from these three primitives. And really what we're creating is a trading floor where autonomous agents can barter with each other, which is a massive unlock for a lot of applications, particularly in multi-agent systems. So the long-term vision is from these basic starting points, what we want to create enable a few things. So the first is a programmatically interactable agent-to-agent commitments. So this basically says, I have an autonomous agent running on my node, you have an autonomous agent running on your node. We basically want to facilitate these agents making commitments to each other in an automatic and programmatically interactable way, meaning that this can be operated on by machines. It's built for machines. It's not necessarily built for humans. We, of course, naturally want to facilitate a lot of kind of the literature that's been lying dormant around in game theory. And so that, includes older stuff like coalition formation, resource and skill-based games, cooperative AI, and some newer fields like compositional game theory, which are composing games as parts of other sub-games. We're really creating the foundation for the cybernetic economy and multi-agent systems. We have okay, I'm gonna like 30 seconds, I'll finish. So cybernetic economy, multi-agent systems, and then naturally, what we really want to kind of be able to facilitate is the coordination of highly complex games, things like scientific knowledge creation, and really create economies around that. Something that I'm personally interested in is public goods computing. So for those of you who are familiar with SETI at home or folding at home, it would be something like tokenizing those projects and then creating something like futures markets for the best use of idle computing power, which is a really fascinating idea. So yeah, the key takeaways, programmable money needs programmable markets. We have programmable money. We do not yet have programmable markets. We are basically building a trading floor for autonomous agents, and composable markets and games will underpin the future of multi-agent systems. Thank you so much.
Awesome. Lots of interesting mechanism design related questions I want to ask, but first we will move to other panelists. So next we have is Varun Mathur. Varun is the co-founder and the CEO of Hyperspace, which is building a breakthrough new generative browser powered by a network of consumer nodes. In 2024, Hyperspace has built out the world's largest distributed Uber-like AI network with its own proof of flops-based economy running hundreds of nodes, developed a novel reasoning model which can break prompts into an interconnected directed acyclic graph, which utilizes open source models, a 3.2 TB vector database, and a consumer AI product which brings all this together. The combined effect of this is lowering the price of complex AI systems, such as Claude or Perplexity Pro, to being a function of local electricity cost and real-time market dynamics, making AI more accessible around the world. We are very excited to hear from Varun. Please go ahead.
Sure. Thanks so much. Thanks so much for having me as well. I'll try and keep this quick. I'll try and keep this to demos, things which work. I think we all believe in decentralization, why it's relevant. Like a quick rundown on this, like why we are doing this. It's from a very consumer first perspective. And really the inspiration there is when search engines first came around, we had things like AOL. People say, hey, look, we big companies alone can figure out the best way for people to get information. And people, while that excited a lot of us, that also we realized the right way was decentralized, distributed discovery of information, right? So the advent of search engines. And I think from a consumer perspective, a similar story will play out for AI as well, right? So what we have seen so far excites us a lot. I just noticed like half an hour ago, there's some tweet about Strawberry and so on. So there is massive movements from big closed AI companies. And the question is, what's the end game, right? Do we want to look at a word processor with everything filled out, or do we want choice? Do we want freedom and the ability to tweak, right? So we've been, at Hyperspace, just kind of approaching this from a few different perspectives. How do decentralized networks work? How do you incentivize nodes to join? How do you do n number of other things? And the end goal is, can there be a complex AI system which offers the right choice and power to users, which still leads to comparable results, what you can get from a best closed model out there, right? And that's been our research and product direction. So what I have on the screen here is just like one inclination of it, right? And this is a product live on compute.hyper.space. And what you're seeing here is an interplay, right? Firstly, you give it a prompt, we fine tune a model, which breaks down that prompt into a DAG, right? So it's a DAG of connected agents, and each agent can have different capabilities. You can define how they work. And the more interesting thing is you can actually choose that for certain agent, I want it to run using Llama 3.1. Some other agent, I might want to use CodeStral to generate code. And the idea is that we are going to live in a world where there are going to be many, many models, right? Hundreds, thousands, tens of thousands. And these models increasingly running on regular consumer devices. With the choice being with the users in what model you use in what scenario. And not just that, if you can also choose data sources, and that again comes from really an intense effort around trying to provide the right, if you want to use Wikipedia, do you want to use Reddit or some other data set? If you have choice around that, and you can also do web search, and you can also do code execution, and you combine a few of these primitives, and that's when it starts getting into a rather interesting territory where you as a user, you don't have to pay, and you don't have to be in a specific, $20 a month professional plan. So why decentralization? Again, can this provide a comparable or better experience? And secondly, can this also be a lot cheaper, right? So when we, our interest and mindset is, if you're a college student in India, in Manila, elsewhere in the world, you don't have $20 a month, right? You still want the power of complex AI, and it's a function of not just the model, but the data set and a number of other things. How can we use decentralization? How can we use all these tools available to us from a software perspective to reduce the cost of complex AI to your cost of local electricity, and along with the any market dynamics, right? If the system is getting inundated and so on. So, there are, some products, some a number of things. We built out this live peer-to-peer. It's a distributed Uber-like network. There's a server which matchmakes nodes. A regular consumer node can still run the inference and get the results back. And the interesting thing is there are many models, and we don't want to be in the zone of choosing the models for people. It's if it's a large network, and as long as we can provide the right information, users can make their own choices here. So and there are different parts to this. Why would you want a server model? And we are introducing and done some work around essentially inspired from proof of work. We send a challenge every hour to a node which is pledging certain amount of VRAM. And if you can solve that challenge, then you get certain rewards. And if you fail the challenge repeatedly, then you're slashed. So this system again is silently live today. If you run a client on your desktop, or even if you just run it in your browser or on the command line or elsewhere, you can start participating in this. And the idea is that even the UIs which you're using, can you then spend the rewards which you've earned here into different types of interfaces to actually leverage these different networks. So I'll pause there if there are any questions. Happy to take on a few different things there.
Pretty cool. And for people who have not tried, the demo is actually, I mean, the actual interface itself is really cool. So definitely give it a try. And we will take questions later, but let's quickly move to the next talk in the panel. And last but not the least, we have Rand with us. So Dr. Rand Hindi is an entrepreneur and deep tech investor. He is the CEO at Zama, an open source homomorphic encryption company, and an investor in 70+ company across cryptography, AI, blockchain, and biotech. Rand started coding at the age of 10, founded a social network at 14, and a web agency at 15 before getting into machine learning at 18 and starting a PhD at 21. Wow, okay. He then created Sniffs, an AI startup that was acquired by Sonos, as now powering the voice assistant over 20 million devices. He has been elected as TR35, Technology Review 35 by the MIT Technology Review, as 30 under 30 by Forbes, and was a lecturer at Science Pro in Paris and an advisor to multiple companies. He was previously a member of the French Digital Council, where he focused on AI and privacy issues. So very excited to hear from Rand. Please take the stage. Thank you.
Hey guys, nice to meet you all. Can you see my screen?
Yes.
Great, excellent. So I apologize, I'm not going to give a technical talk today. I thought it was supposed to be more of like a very high level talk, but seeing the other people before me, I feel that I should have done a coding demo, but hey, next time. So I want to talk quickly about confidential decentralized AI using homomorphic encryption. So one of the issue with decentralized AI is that you're effectively exposing user data and model parameters. So as a company, if you want to use any kind of DeepIn protocol, you have to figure out how to deal with confidentiality. And as was alluded earlier, using TEs, SGX, and things like that is just not going to cut it. So cryptography is definitely the preferred solution here when possible. The idea of homomorphic encryption is that you can compute unencrypted data without having to decrypt it. So imagine, for example, I'm a user and I want to interact with a decentralized protocol that is running on untrusted public nodes. What I would do is I would encrypt my data with a key that I own, so nobody else has the key to decrypt it, send the encrypted data to the node that would process it, so they would have no idea to know what they're processing for me, but they can still run algorithms on it, produce a response which is encrypted that I can decrypt. So for me as an end user, nothing changes. I'm just really using like a service, remote service, but now the data is encrypted when I send it and during processing, so it's encrypted end to end. So within specifically decentralized and DeepIn, there's a bunch of use cases. You can keep your data sets and model parameters encrypted end to end, even during the protocol being run. You can do inference, you can do fine tuning, you can do training, up to a certain level of performance, of course. And importantly, the nice thing about FHE is that it's a very basic client server model. So you don't have to modify the actual protocol that's running underneath. You just have to modify the node that's running the software, and that's it. So we have seen a bunch of use cases being built using FHE in decentralized protocols. So for example, marketplaces is something I'm quite interested in. Today, if you try to build a data marketplace, you're effectively selling the data so that people can use it for, I don't know, training a model. But as soon as they have the data, they have no reason to pay you a second time for using it. They already have it. With FHE, you could sell the result of the computation on your data as opposed to the data itself. So people would run their computation in FHE on your encrypted data, and you would only allow them to decrypt the result, not the data set itself. So you can keep monetizing your data sets as long as people want to use them. Lots of things are in healthcare. If you go to our Hugging Face space, Zama AI, we have, for example, a demo of using FHE to do DNA ancestry encrypted end-to-end. So effectively, you upload your encrypted DNA to a server that does, like an analysis and returns your predicted ancestry. And you kind of get the idea, right? There's a bunch of things like that that's currently being built. There are a number of protocols which are currently implementing and deploying FHE in blockchain. So this is not something theoretical. This is something that is actually being deployed in the coming months. And talking more specifically about how you would use that as a data scientist, we've made a lot of effort at Zama to integrate FHE natively into existing tools that people use so that they don't have to learn anything about cryptography. So here are two examples of how you would use FHE within, for example, scikit-learn or PyTorch. You're really just writing Python codes using the APIs you're used to. The only difference is it's running on encrypted data. So there's not a single line of cryptography or anything related to configuration you have to worry about. This is completely automated. In terms of protocol security, as I mentioned, FHE really doesn't introduce any new security assumptions in the blockchain protocol itself. So you can prove the correctness of the FHE computation like you prove the correctness of any blockchain computation through consensus, through fraud proofs, through cut and choose approaches. You could theoretically do zero knowledge FHEML. I mean, FHEML snarks would be more correct in that sense, but that would be very, very slow. To give you a bit of a sense of how fast FHE is progressing, in the past 18 months, we've made one of the FHE models that we've been benchmarking, CIFAR in this case. So not a big model, but still a pretty relevant one, 5,000 times faster. So inference went from 40 hours down to 28 seconds. And this is purely based on just cryptography improving and engineering improving. What's happening now, though, is we're starting to get to the limits of what cryptography can do on GPUs and CPUs. Roughly speaking, we are at a stage now where we can almost do GPT-2 in FHE for inference. So, interesting, but I wouldn't say that this is, the end game. However, there is a path to running large language models, GPT-3 and above, in FHE using dedicated hardware accelerators. So, the same way that GPU accelerated AI, you're going to have like an ASIC or a chip dedicated to accelerate FHE. So there are a number of companies working on that, including Intel, including ourselves. And the first generation is coming up next year, but we expect that the real acceleration will happen between 2027 and 2030, which is when FHE should start being usable in most cloud applications. So the way that we think about this is that eventually FHE will become a new Internet protocol. So the same way we went from having no encryption with HTTP to encrypting data that is transmitted with HTTPS, the next natural step is to encrypt data during computation, so end-to-end, using something like homomorphic encryption. So we call that HTTPZ, not for Zama, but rather for zero knowledge. But that's really what we're trying to work towards. I think we do believe that there's going to be a point at which FHE will become so cheap and so efficient that you really have no reason not to use it in any kind of blockchain or cloud application. Thank you.
Very exciting talk. And once again, if people haven't tried out, there's some really cool demos. I tried one photo filter on Zama's website. Works really well. So yes, we will put our panelists together now. Let me see where are the others. Oh. Does anyone see? Because my whole view is distorted. Well, now, oh, there you go. Where did it go away? Wonderful. And third panelist is right here. So we will have him on the Zoom. I guess I should pin myself in that case, right? Yeah. There you go. Okay. Cool. So are there any questions on the Zoom? And we can start from there. Or if anyone has any question for any specific panelists, we can start. Otherwise, I'll go first and I'll start in the reverse order. So question for Zama. Oh, yeah. Why don't you come in here? Actually, yeah. Let's do it like this. Okay. So my question for Zama was, so you mentioned GPT-2, like you can already do like a fully homomorphic encryption approach, which is by the way very cool. I think it's around 100 million parameters. So plenty of like computer vision models that work really good are already of that size. So are you seeing any adoption already where people actually want to use these models, not necessarily GPT-2, but models of similar size, but with fully homomorphic encryption?
Good question. So just to clarify, we are on track to be able to support GPT-2 in the next, I would say, 12 to 18 months. Right now, we're still a little bit under the kind of performance. And also to be clear, the benchmarks are against, I would say, like regular GPUs. They're not against, crazy AI accelerators that can do like 5,000 tokens per second. Also, I think, benchmarks, important to be honest about what you're benchmarking against. We're benchmarking against GPUs, not against Grok type accelerators. To your question about whether we see usage, I would say that right now, FHE, you can make inference in sub-second for any kind of more traditional machine learning models, trees, regression models, things like that, which turns out to be used in most applications. 80% of finance, or even more than that, uses basically linear regression models, right? So you can do that in FHE. You can even trade them in FHE fairly well. We're not yet at a point where you can just put FHE in any kind of machine learning workflow. One of the reasons, interestingly, is because of the pre-processing that's needed on the data before you can feed it to a machine learning model. So, like your pandas, data frames, and things like that are actually horribly inefficient to do in FHE. We can do it. We have a prototype of like an FHE data frame, for example. But all of that put together, what you realize is that it's not just the model that matters, it's actually a pipeline, and that's a little bit more complicated. So what we found is that decentralized protocols, decentralized AI, decentralized finance, decentralized smart contracts, all of that is where there is most demand for FHE right now, because there is no choice. It's either you use FHE for confidentiality on those decentralized protocols, or you just don't build use cases where you can't afford the data to be public. So this means that you have new revenue from FHE in decentralized protocols. In traditional clouds, people still use those products even without confidentiality. So companies aren't willing to invest in something even that's 10% more expensive. So we need to make FHE cheap enough and fast enough before it economically makes sense for someone to use it in Web 2 and cloud applications. So it's not that people don't want to use it, it's that the incentives in Web 2 are not the same than in Web 3, where people actually want to build new things with it.
Yeah, and I believe your analogy with HTTPS and then going forward HTTPZ would make sense in that similar way, right? Where HTTP was like the majority of the web traffic, but now that has become so cheap. And
exactly. If you told someone in 95 that they would encrypt all web traffic, they would be like, no way, right? Like the cost of doing that is way too expensive. And 20 years later, it became the default. And I think it's going to be the same thing with FHE. The nice thing is that we've solved most of the math problems. Now it's just compute and speed, which fortunately is easier to scale than science.
okay, so let's move to hyperspace. My question was, and this is something I'm personally also working on lately, like you have, when this is a totally decentralized ecosystem, you have lots of nodes that could be unreliable. Some nodes might be like not as efficient in terms of communication, so they might be stragglers and so on. How do you think about the orchestration problem, and do you see any like technical challenge there?
Yes, I think many. I think it's a fundamentally very hostile environment. Nodes coming offline or online, different types of nodes, different types of models being served, and so on. So we are trying to take a progression here, we wrote papers about how to build decentralized AI protocols, but then practically what we started with is said, okay, can we start it as a controlled experiment, and where we do have a server, where we do have a way to challenge these nodes and see what's their actual capability like. And we can give them a reward if they are, someone signs up and then they go offline after that. Can we then slash them? So what are the base incentives, and we assume the nodes will follow. And the incentives as laid out, a node is incentivized to provide as much compute as possible, run the strongest model as possible. So our goal here is to nudge nodes to run the right models. Code Shell came out. If there are a large number of nodes running that's great. If most nodes they do bring a lot of compute, and if they're running some random outdated model, that doesn't help the users, that doesn't help anybody. So it's around nudging through the incentives at play in how do you run the right model? Can you bring the right compute? And if you're doing that, do you also stay online, right? And how do you make this work? Because if you just have 5,000, 10,000 nodes as part of any decentralized or any peer-to-peer network, it's not interesting, right? You need much bigger scale. And at that much bigger scale, you will not be able to use just cryptoeconomics to incentivize 1 million nodes to be online, right? So you're going to need more utility. You're going to need, I think the parallel there is with BitTorrent, right? BitTorrent saw more than 100 million clients at one point. And people were not waking up thinking that, hey, look, I really want to be a seeder today, so let me start this application and run it. They wanted a specific utility out of it. So, and I think this is where the idea of a generative browser, of the one universal canvas, where I as a user can go in, try and get some utility out of it. I can generate some action, have some agents run something for me. If I'm getting some utility out of it, and a node is part and parcel of that experience, I think that's how the actual peer-to-peer network kind of forms. And even in that, there would be different choices. There would be a set of folks who would say, I want to join the broader distributed network, run things for me, and I'm happy with that. And then there would be some who would say, I don't trust you at all. I'm going to run my own cluster, right? Just give me the software. I care about complete privacy. And there would be those sets as well. And then on the furthest end would be nodes which will say, look, I don't want to run my own devices, but I do want a completely permissionless system. And that's where your decentralized trust comes into play. So at each step of the equation, you as a user are making certain trade-offs, right? If you want a fully decentralized system, you're paying more in terms of cost. You're paying more in terms of latency. And if you want a different experience, then life's about the choices you make as a user. The intent or the goal is how do we get abundance of protocols, abundance of cryptoeconomic schemes or incentives, and abundance of models, nodes. I think if we are in that world, that's how we can provide a competitive, and not just a competitive, I believe a better solution and better alternative to what we are seeing from the top closed AI companies today. So not sure if that helps answer, or I could have gone on a rant.
I guess two big themes I see emerging. Sorry, I should start. One is trust, the other is incentive. And speaking of incentives, one question I had about the whole Coup5 approach is, so a lot of these like game theoretic mechanism design problems you guys are looking at, typically people make assumptions about these agents that they're acting rationally and those kind of approaches, which might not be true in the real world. How do you think about that?
Yeah, so that's a really good question. So basically, so let's go back to the problem of like verifiable computing, just to be very specific. You wanted to assume the kind of idea was, okay, we want to stop people from cheating, right? We want to stop people from actually like giving back the wrong results in this kind of peer-to-peer network. And in order to do that, we basically want to, what's the rationale behind even doing that? And to begin with, it's because you're going to make more money, right? It's cheaper to just not do the computation, not spend the money on the electricity, and just give back a fake result. So the primary motivation is financial in this situation, which is why this concept of utility maximization and training agents to maximize utility works, right? You're not assuming maliciousness, you're just assuming utility maximization. Now, in terms of what happens when you do have malicious agents, that is a really good question, and that really depends on the specific context and what the action spaces of those agents are. Naturally, of course, you have things like, well, if those nodes are identified by their public keys, you can have a reputation system where people can either local or global, where people are just ranked by like what they're due, like how much do other people trust them. So you can have a web of trust approach. In some cases, you can like obscure the contents of transactions or data that are being passed. I mean, FHE is like a really good way to do that. There are, but kind of more to the kind of like really kind of deeper philosophical question, which is like, okay, we are now going to be, we're entering a world of autonomous agents, right? We are entering a world of multi-agent systems, and some of them are actively going to be malicious. We can predict with almost near certainty, in fact, it already happens. Governments and non-state actors are manipulating elections using large language models and agents. That's only going to get a lot worse. And you could do a lot worse than that. You could do attacks on financial systems, on energy grids. There's all sorts of really malicious behavior that you can really tackle, can do in these environments. And so we have to be really careful about that. My kind of high level opinion is that like an overview, like 30,000-foot view, is that we're going to have good agents fighting bad agents very, very soon. And we need to prepare for that eventuality. And that basically that's going to involve a painful process of both research and like actual production engineering. Yeah.
Awesome. Thank you so much. Looks like lots of interesting challenge ahead of us, but there are so many great companies which are going to take care of these problems. But for now, we will wrap it up here. Let's thank all of our panelists again, and we will release the recording very soon. And yeah, let's stay in touch, and looking forward to hosting all of you in the next Roundtable.
Thank you.
Hi, guys.
Thank you.
Thank you.
The next lecture